Uh, Hello, my name's Talon. I'm going to give a talk about programming mathematically. How many of you have told one of your non-developer friends, you're like, oh, I'm programming, and they're like, oh, I could never do that. You must be so good at math. Yeah? And you're like, I've failed algebra. I don't know what you're talking about. Well, there's a lot of math in programming. I'm going to show you how we can utilize it and maybe learn to hate math less, because maybe everybody in here hates math. I know I did. Just a quick note, if you want to follow along while I'm doing this, skip ahead and give out spoilers before I get to them. This is live on the internet right now. The ghost in me / you must be so good at math. And there's a repo. So this is me on the internet. Some of you are like, oh, that's him. He's the ghost. And some of you are like, oh, I should follow this guy. He looks really cool. Yep. So there's one secret to becoming a mathematician as a developer. And does anybody have a guess what it is? Cool. It's using pure functions. This is the genesis of all mathematical programming, or all functional programming, is using pure functions. So you might be wondering what a pure function is. I'm here to answer that question. So a pure function is a function that for the same input always returns the same output. So if I pass it a 1, it gives me a 2. The next time I pass it a 1, it better give me a 2 or else it's not pure. And it also has no side effects. This is sort of implicit to giving the same output, because if you have side effects, that's an output that isn't expected. So to get a little more familiar with purity in our programs, we're going to look at some functions that you might already be familiar with in JavaScript. And let me see. Cool, that's a little bigger. So math.random, can anybody tell me, is this a pure function? Does anybody know? It isn't. Yeah? It's not. It's not a pure function because if I call math.random, it's going to give me something different probably every time. It'd be really weird if it gave you the same thing every time. What was that? Right, right. So math.random, not a pure function, so we shouldn't use it in our mathematical programs. Yes?
Would you really say it's not a pure function? I mean, given that it uses some sort of entropy value for the randomized value that it generates, as long as that entropy value is the same.
Yes, you're right, and there are ways to functionally do a random value. The math.random function, just for this example, is explaining how a different output given the same input isn't pure. But there are ways to get around randomness in programming. Yeah?
I mean, the input to math random too is like the unit, so it does take the input and it doesn't get the same output. So that would.
Right. So math.random, not pure for our sake. Console log, does anybody know if this is a pure function?
Yes.
It's not a pure function because it alters the world. It's the dirtiest of functions. It mutates the console, and so not a pure function. Disgusting. How about these? In JavaScript, we have unshift and push on the array prototype. Are these pure functions? Does anybody know? I'll tell you they're not. Yep, they mutate the array. So if you give it an array, everywhere else in the program, that array is going to get mutated. That stinks. Slice. Totally a pure function. It gives you back a new array for, or a new part of the array that you want. And this, you might not be able to see it. This is a little plus sign. And you might be thinking, isn't that a binary operator? And yeah, in JavaScript it is. But addition is a pure function, right? Every time you give it 1 and 3, you get 4. That never changes. And if it did, we'd be in trouble. So this is how you become a mathematician. All of the functions have to be a mathematician programmer. All the functions have to be pure. So this gives us this limitation, this restriction, which essentially boils down to immutability. If you can't mutate things, then you have immutability in your program. So let's look at, now that we are mathematicians, let's see how we would write programs. So we're going to look first at how to write a function. And these are some guidelines that if you follow these guidelines, you will get compositional functions that lend themselves well to currying, which you'll see a little later in my example. So the first rule is to take the data last. If we're operating on an object or an array or a number or something, that should be the last argument to the function, and all of the things that you want to do to it should follow that. This is so that you can do like point-free form and whatnot, but that's a little ways down the road. Never mutate. So mutation is a side effect, and it's impure. So in this example, we're going to extend an object, literal dog, essentially clone it by giving it all the properties of the dog that gets passed in, and then update it with all the updates on that update object. So we'd never mutate the dog object itself. We just return like a representation of what the dog object ideally should look like after we run this function. And the other thing is you should do one thing well. So it seems like if I want to feed and walk a dog, I could easily write a function that does that. But if we do one thing well, then we get a bunch of tiny little Lego blocks that lend themselves really well to the final thing, which is compose. You should, when you're writing programs, you should seek to write a function. You should seek to find a function that already does what you want in a library somewhere. If you can't find one, you should write the very minimum, do one thing well, and then you should compose all of the do one thing well functions into a function that does the larger task for you. And this is what your programs will end up boiling down to, is a huge composition chain in functional programming. So this example here, we're doing a manual composition. We'll see some utilities in a minute to make it a little easier. But you can see we first feed the dog, and we pass the dog that's fed to walk dog. So it's going to go in that order from like in, out. Which is how you do that. So there's some utilities for this. In JavaScript in particular, there's Ramda and Lodash-FP. You might be familiar with Lodash, maybe less familiar with Ramda. Lodash-FP is the Lodash you're familiar with, like the underscore Lodash you're familiar with, but the data is taken last. The functions are first, right? So that you can lend yourself to this functional programming. And all of the functions are automatically curried, which we'll see an example of currying in the examples. Here's how, given Ramda, I would make a composition. So this is my app. I want to pet, feed, and walk a dog. So I made a dog app that does that. And quick quiz, what order do these functions get called in? Does somebody know? Yeah. Yeah, and in this case, because I wrote it from bottom up, and this would definitely not work because I put a comma inside of a function, like at the end of the argument, so syntax error. But yeah, pet dog, feed dog, walk dog. That's the order it'll get called in. Then we get a function that's just waiting for a dog. And we pass it in here, and we get a dog that's petted, tired, and fed. Not hungry. Cool, so when you're going through your programs, like this is all neat, but eventually you're going to want to like have side effects. For example, we're going to take a look at how do we throw an error in a pure way? How do we handle a null value in a pure way? Because if we just use JavaScript null or throw is similar to console.log. It mutates the world. It crashes our program, logs to the console. It does all kinds of nasty effects. Let's see how we can do that in a functional way and see if we like it. I'm not here to sell functional programming to you, but I'm here to introduce it. Maybe you'll like it, right? So one of the tools we're going to use in the examples is map. Who here is familiar with array.map? Okay, so a fair amount. If you're not, this is what it boils down to, right? You call .map on an array with a function, and I'm passing it our dog app, and it applies that function to every item in the array and returns a new array. It's a pure function. It returns a new array. Does that make sense? Cool. So let's think about map in a more abstract way. Map kind of transcends arrays. We can map over other things, and we're going to take a look in our examples at two types in particular, maybe an either. So the definition of map here is it takes a function and applies it to the value inside of a type. So if we think of arrays are a type, right? It applies the function to all the items inside the array type. Here we have a maybe type, and there's a value inside of it. If we map over a maybe, it applies that function to the value inside the type. Brain melt yet? A little bit? Okay, we're going to go over some examples and hopefully clarify it, but this is definitely stuff that hopefully you get inspired and sort of dig into it a little more. The either type does the same thing, and if you look at this example here, you can see a pattern. you can think of just and right as types, and you can think of resolve as a type as well, of a type of promise. And it's just applying the function inside that type. It's like literally visually inside that type applying that function. So that's a core idea behind map. Then there's an apply. An apply is like the inverse of a map. This one is even more brain bending, but hopefully we can sort of wrap around it in the examples. It takes the function inside of a type and applies that to the value that you give it, right? So in this example here, we have add, which is a curried function. It takes an argument, returns a function that expects another argument, and then adds those two together, right? So if I have a just and I map add over it, then inside that type, it says add 1. And add 1 returns a function that's expecting a b. So this is the same thing, b 1 plus b. It's expecting a b inside there. But because it's not a typical JavaScript function, we need a way to apply a value to that function inside the type. So that's what app does. It applies 4 to the function inside of the type, right? So this boils down to just 1 plus 4, which is just 5. And we're going to see the utility of that in the examples. So let's do some examples. Okay, so given the use that we want to create like a function that returns a full name given a first, middle, and last name in like a fancy formal format, I'm going to start by writing this initial function that takes a word, because I want to just have the middle initial. It's going to take a word. Live coding, you know. Split it, and then get the first value inside that word, right? So that'll give us if we give it a word, it'll give us the first letter of that word. I'm going to create a full name function, which takes first, middle, last, and this will return, we want to show last, initial of the middle, period first. Cool. So yeah, that's that function. It's a very basic function. You've probably written something similar, maybe not full name, but you've worked with strings before in this manner. So we can do something like, real quickly, I'm going to define an alias to log. If I log out a full name here, Rachel, Sarah, that's her middle name. Lopez. Cool, so we can if we did it right, it compiles and then we get Rachel, Sarah, Lopez logged out. Pretty boring. Let's make it cool. What if we don't know if we have all of the values for the full name? Let's write a function that let's go over currying first, actually. So currying takes a function with multiple arguments and breaks it up into a function that returns a function of the it breaks it up into a function of unary arguments, so one argument. So if you have, we'll see the example here. If we have full name, we can either give it all the first, middle, last, or we can partially apply it with the first name, and then we'll have like a function that accepts Sarah's middle and last name. I got to import the currying library real quick. So now I can write full name Sarah, and this is a function that will take Sarah's middle and last name, right? So I can do log Sarah name, Rachel as Sarah's middle name. It's going to blow up. From? Yep, you're right. Thank you. Yep, so we saw that we can partially apply Sarah. So this Sarah name returns a new function. That's what currying does. All of the values when we're functionally programming, we're going to want to curry them. So you can use this curry function, or Ramda and Lodash-FP also have a curry function that you don't have to supply the arity of the function, right? You can try to do it without currying, and you'll experience for yourself why the currying helps. Let's write a full name maybe. We're just going to call it full name M. That takes first, middle, last, but it's going to accept the maybe type. And it's going to map over that with the full name type. So this is a process called lifting, and there's a faster way to do it. We're just showing the implementation here. We want to lift full name, or first name into full name, and then give it the last name. And so now, if I have a potentially null value, let's start copying and pasting now. Maybe gives us just and nothing. So just means that a value exists. Nothing means that a value is null. And we'll see why you would use that instead of null here. So this depends on us applying this type to here, which would be kind of the equivalent in full name. We can think of it as like string, right? But there's like a literal way to say the word string in JavaScript. So we can just shorthand to the string quotes. But for custom types, like maybe we're going to have to say specifically what that type is. So full name, we give it a bunch of justs. This time it's Alice. And we should get, if it doesn't blow up, oh, we got to log it out. ToString because this is a custom type. Can you see it there? Yep, maybe just Lopez or Alice. So we got a value, but if it was potentially null, if we were to give like a null value to, there we go. If we were to give a null value to that full name function, the program would crash, right? Because it would say like you can't, or it'd give you a weird result back. It would add null to a string, which we wouldn't want to do. So we're going to just say in this case, if any of the values are null, then just give us back nothing. So don't do anything. So now we can operate in our program compositionally and worry until the very last moment to handle a nothing. So we can just assume everything went all right, don't have to write any try-catch statements or anything, and when it comes time to like actually extract this value, we'll check like, is it nothing? Okay, then we should throw an error, appropriate error to the user, or if it's just, do what we wanted to do. Does that make sense? Does everybody see the utility in that? It's a little wonky. Okay. So what if we want to throw like a more appropriate error? Instead of just nothing, maybe we want some information about why it failed. There's another type called either. And the way either works is it's there's a left side and a right side. and the right side has a bias. There's a bias for the right side. So any operations that are a right side, it's going to apply the functions to the right side. The left side is like a default value or an error value that you can supply. So what's really neat is that because we're following the spec with the map and the apply, we don't have to change our full name M function at all in order to identify the side effects that our program might have here. We just have to give that function the types that we might, or that it, the types that identify the side effects we expect to have, right? So we can say incomplete. I'd say full name, but that's a lot of typing. So now all I did was change the types that get passed to this function, and I'll get back a new side effect here. And now we have a more descriptive reason why our full name function didn't work. It was incomplete. You could do the same thing if you do a little tomfoolery with the promise type. If you wrap it in, you have to give it a map so that it follows that spec here of map and apply. Any object that has a value that's mappable and applicable, you can pass to this function now. So it's super generic. You can express the side effects that you want without having to rewrite the program in its entirety. Does that make sense? Sort of? Kind of weird. Cool. So this map and this apply thing is sort of abstract. It might help to implement it ourselves. So the JavaScript string primitive doesn't have a map and an apply type. Which kind of sucks because maybe I want to pass a string into full name M and then completely get rid of my full name function that expects a string, right? So that I don't have to sort of toy around with these primitive functions and these lifted functions. So let's do that. So the only time in this functional world, this mathematical world, that we should be writing constructors or classes in JavaScript is to identify a type. Let me give you an example to sort of solidify that idea. If you want to create a new string in JavaScript, you can do it this way, right? You can say new string. So it's like kind of giving a class, but we know string is a type. You can do the same thing with array. So why can't we make our own type called string plus, right? And that's what we're going to do. We're going to create a new string plus that follows this mappable, applicable protocol. So call it string plus. It's going to take a value. All of these types are going to wrap a value, right? So we're going to set this.val to the value inside the type so that it can carry it around and know what to do with it. Here's a quiz. Start thinking now while I'm typing. How do I implement map on this string type? Can anybody recall the definition of a map? We're just going to take a function. We'll call it f. And we're going to apply f to this.val inside of the type, and we're going to return it. That was like super simple to do, right? Easy conversion. Now we can map over this. We can already lift it into a function. Let's see how we can give it the apply protocol or spec. So we're going to just copy this function here. So the definition of apply is apply the value given, or take the function that's inside the type and apply it the value that's given, right? So we're going to take a value here, and who knows what might go into this slot here. This.val is a function, and we apply it to A. Does that make sense? Cool. So yeah, this relies on a function being inside the type. So as a developer, you have to know, don't apply something that there's not a function inside that type. And you can like utilize some sort of type system, I'm sure, to do that. And then just so that we can like inspect this a little more sanely, let's give it a toString that takes nothing, and this will return. So one important note here, you'll see in these other slides or these other examples, I didn't use the keyword function. I was just using the fat arrow in ES6. You have to use function here because you're going to be lexically bound to the this inside the constructor, right? If I used a fat arrow, this would be the window value or the global value. Just a trick that you'll probably run into and then debug for a while and then go, oh yeah, Talon said this is going to happen. Then you can hit me up and say thanks.
You could still bind the context though, right?
Uh,
There's a way of using a fat arrow to bind the context.
yeah, I think you can do that if the fat arrow has a .bind method. I've never tried that. Yeah, that would probably work. So, okay, cool. We just we did that. That was pretty simple. And now let's play around with it a little bit. Last example of the day. Hopefully mines aren't too melted. So I've just created this alias for map up here so that I can give it a thing that is mappable and not have to chain off of that just because. So we're going to create this punctuate function that takes, who can tell me what this might take? This is sort of a DIY part of the talk. So what's our data that we might be taking in this function if we're going to punctuate something? Maybe a string. I don't want to call it string. Maybe I'll call it message, right? So if that's the data we're taking, where should it go in the function argument list? Right. So the first thing should be the punctuation to apply, and then the message. Punctuation. Yep, good at math, not spelling. So that makes sense, right? Message plus punctuation, that's how you punctuate something. Let's level it up and curry it. This might be a more solid example of where currying can be nice. Because now I want to write a function called exclaim. How would you write this function? Yep, partially apply punctuate with an exclamation point. So now I have an exclaim function that's just waiting for a message. Does that make sense? Cool, awesome. All right, so I've already imported our string type. We're going to write a function called greet, and we're going to have person A greet person B like this. Hello, name B, said, name A. All right, cool. We should probably give it the name A and name B arguments, right? So now I can say greet, I want Sarah to greet Rachel. And then we'll get, hello, Rachel said Sarah. Let's curry this, because we just want to curry all of our functions for utility. Now we have this elevated string type. Let's see how we can use it. We implemented it. Maybe it's not working. We can write tests, or we can just try to use it. In this case, we're going to try to use it. You should do both. So one thing we forgot to do in our string type, because we don't want to think about classical inheritance in our domain code. So this is a trick to making it so we don't have to use the word new. We're going to take a value and just export a function that returns string plus with that value, right? So now over here, we can just say string plus A, and we'll get a new string plus A. Because new is just kind of gross. Let's not use it when we don't need to. So we can say string plus Sarah, and does anybody know how I would get Sarah to, because we have this new type that needs to be lifted into greet. What function would I use on the string plus prototype to get this to get into greet? I wouldn't use apply yet, map. I would use map because it's a value that I want to apply to the function. So I want to give this value this function greet. Now is apply, right? I want to get Sarah to greet we'll say apply string plus Rachel. Cool. And we can then call toString on this and log it out. And if it doesn't blow up, sweet, it didn't blow up. We said, hello, Rachel, said Sarah. So we just lifted our string plus value over that function. Neat. Any questions about that example? This is the end of my talk here. Here we go. So a few things to note. There's links in these slides that you can find at this URL. I'm not sure if the full thing's showing up. That there's some people said this better than I did. I'm just trying to translate the way they taught me, right? So there's some links at the end here. Folktale is the library I was using for data.maybe and either and core.lambda. Fantasyland is a JavaScript algebraic specification. This is where you learn what map is. I'm going to tell you right now, we all just like used monads. That was a thing. You didn't even know it. They're like not hard. So yeah, map is a functor. Something with a map is a functor. This is where you learn that is that Fantasyland specification. And it's good to couple that. It's like super generic, so it's good to couple that with examples. Hey underscore, you're doing it wrong is a good argument against underscore and a good argument for Ramda and low-fp. Brian Lonsdorf, he's a really brilliant guy. And a monad in practicality is by this girl online that goes by Robot Lolita or Sorella. She does a great blog post about sort of what we went over here using either, but she goes over the more low-level monadic properties of it. She uses, in Fantasyland, there's a chain spec and an of spec, which is what defines a monad, but you can create map and apply via chain and of, sort of some tomfoolery going on there. So thank you.